Namaskar. I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss with you inner product space from the subject linear algebra, inner product space, second topic. And in inner product space, to unities or sub to unities. Algebra and associative ring definition of algebra. Definition of algebra now see here. An associative ring A is called an algebra over here if A is vector space over here so that for AB belongs to A and alpha belongs to here, alpha of AB is equal to alpha A multiply B or alpha of AB or alpha of AB or A multiply alpha B. This is A is called algebra over F. Algebra over F. Now one more remark. Homomorphism of Phoebe. Homomorphism of Phoebe is an algebra over F. Is an algebra over F. We denote if A of Phi is algebra of Phi, and whenever we want to roles of the field F, we shall denote it by AF of V. AF of V. Next definitions linear transformations on V over F, or linear transformations on V over F is an element of AF of Phi. A of Phi is the ring or algebra of linear transformation on V. Next lemma or theorem. If A is an algebra with unit element over F, then prove that A is isomorphic to the sub-algebra of A of V for some vector space V over F. Now for the proof, it is given that by hypothesis A is an algebra over F. It must be a vector space over F. It must be a vector space over F. We shall use V is equal to A to prove that this lemma. Suppose that A belongs to A, small a belongs to A, and define a mapping TA from A to A by T of Phi is equal to VA for all Phi belongs to A. We assume that TA is a linear transformation on V of A. We assume that TA is a linear transformation on V of A. By the right distributive law, TA of V1 plus V2 is equal to V1 plus V2 into A. By the definition of mapping, V1 plus V2 multiply A, distribute over A, V1A plus V2A, and TA of V1 plus TA of V2. Therefore, A is an algebra. A is an algebra. TA of alpha V is equal to alpha VA is equal to alpha multiply VA, and VA is nothing but TA of V. That is alpha TA of V for every V belongs to A and alpha belongs to F. Then TA is indeed a linear transformation on A. Consider the mapping psi from A to A of V defined as psi of A is equal to TA for every A belongs to A. We have to prove that psi is an isomorphism of A into A of A. we have to prove that psi is an isomorphism of A into A of V. Firstly, we have to show that psi is a homomorphism. Firstly, we have to prove that psi is a homomorphism. Now consider A is equal to B, therefore TA is equal to TB, therefore psi of A is equal to psi of B. If AB belongs to A and alpha beta belongs to F, then for all V belongs to A, TA alpha A plus beta B of V is equal to V of alpha A plus beta B. Alpha of Va plus beta of Vb is equal to alpha T of V plus beta Tb of V is equal to alpha Ta plus beta Tb of V, and Ta and Tb are linear transformation. Therefore this is proved. Therefore T alpha A plus beta B is equal to alpha Ta plus beta Tb, and therefore psi is a vector space homomorphism of A into A of V. Therefore psi of alpha A plus beta B is equal to alpha psi of A plus beta psi of B. Now AB belongs to A. AB belongs to A. Therefore TAB of V is equal to U of AB is equal to VAB is equal to TBTA of V is equal to TATB of V is an algebra associative law in A. Therefore TAB is equal to TATB. Therefore psi of AB is equal to psi of A multiply psi of B. Therefore psi is also a ring homomorphism of A. Therefore psi is a homomorphism of A as an algebra into A of V. Now kernel psi is equal to A belongs to A such that psi of A is equal to 0. This implies that psi of A is equal to 0 and TA is equal to 0. This implies that TA of V is equal to 0 for all V belongs to V. Now V is equal to A and A has a unit element E, and TA of E is equal to 0 and 0 is equal to T of E is equal to EA is equal to A, that is A is equal to 0. Thus the kernel of psi must consist of 0. Therefore psi is 1 1 and dimension of A is equal to dimension of A of V, that is vector space. Therefore it gives psi is onto, and thus psi is an isomorphism of A into A of V, and this way complete the proof. Now one more definitions. If V is a finite dimensional, T belongs to A of V, some polynomial Q of X exists for which Q of T is equal to 0, a non-trivial polynomial of lowest degree with the property P of X exists in F of X, we shall P of X a minimal polynomial for T over F. If T satisfies, then P of X divides H of X. Now one more definition. An element T belongs to A of V is called right invertible. Definition of right invertible. Now see here, an element T belongs to A of V is called right invertible if there exists and delta belongs to A of V so that Ts is equal to 1, where 1 is unit element in A of V. Similarly, we can define left in verify if U belongs to A of V such that u multiply t is equal to 1. That is, if t multiply s is equal to u multiply t is equal to 1, then t is invertible. T is invertible. Definition, one more definition. An element t in A of V is invertible or regular if it is both right or left invertible. That is, if there is an element s belongs to A of V such that s multiply t is equal to t multiply s is equal to 1, where we write s as t inverse. S as t inverse. Now one more example. An element in A of V which is not regular is called singular element. Let A be the field of real numbers and V be the f of x is the set of all polynomials on x over F. Therefore, t multiply s is equal to 1. T multiply s is equal to